Look at exam 2 from 352. So for this one, the main theme of this was the SN1, SN2, E1, E2, so substitutions and eliminations. Big thing here people messed up was give the product and type for the reaction below. You will use each reaction type only once. Right? So the types are E1, E2, SN1, SN2. So the biggest thing you had to identify here was, first of all, you had to look at the alkyl halide, right? There's a process to this. You take a look at the alkyl halide. The alkyl halide here in this case is a secondary benzylic, and it's the same one in all of them. All right, that's the same alkyl halide in all of them. Same leaving group in all of them, same iodide. All right, so that's the same. So what we're going to have to look at here is the base or the nucleophile, and that's going to help us determine which type of reaction it is. So things with negative charges are reactive. These two right here. That would indicate to me, make me think more about SN2 or E2, those one-step mechanisms. So these I can narrow down between SN2 or E2 for these two. The harder part is, well, which one is it then? So what else is different about these things? Right, so the biggest thing I always think about is find the differences. Right? So first thing we did, we identified these all as the same alkyl halide, same leaving group. Then we looked at these. What's the difference between these four? Well, these two are charged. Some of them are charged, some are not. If things are charged, they're more reactive. That should tell us one-step mechanisms, E1 or E2 or SN2. Now, what's the difference between these two charged things? Well, this one looks bigger. This one looks smaller. So that would tell me this is probably more likely to do elimination because the SN2 reaction needs that backside attack. The bigger it is, the harder it is going to get to that sigma star there. So I would say this is E2. E2 means elimination. You look for beta hydrogens. So alpha, beta H's are right there. I draw the E alkene because that's usually the more stable one. I minus and left over amine. This one's a little different. SN2, we got to be thinking about inversion of stereochemistry. The leaving group's already in the plane. That's great. Don't need to change the wedge or the hatched. Put the nucleophile there. I minus sitting there. Nice. What about our less reactive bases or nucleophiles? Again, what's the difference? Bulky, non-bulky. Bulky things make me think more about eliminations, just because, right, it's going to be harder to do. Even if this was a carbocation right here, it's going to be harder to get there. And notice these can all become carbocations, right, because they're benzylic. They're secondary and benzylic, not just secondary. There's resonance stabilization there. Again, E1, we can get the trans alkene, or the E alkene. And in this one, in SN1, right, you're going to form a carbocation, so you're going to get both enantiomers, right? You start out with one enantiomer, you're going to have the racemic mixture, which means you have both enantiomers. Whereas SN2, right, you went from one enantiomer to the other. So for the second one here, it's asking you to rank the electrophiles from slowest to fastest in an SN2 reaction. So the fastest, so SN2, we just got done talking about, that means we're going to do a backside attack in a sigma star. So we want something that's not very sterically bulky. So the least sterically bulky here is this bromomethane, right? So that'd be the most reactive. This has one more carbon. So these are primary, secondary. Bromines stay the same. The level of carbons, they're all still primary, but this has more carbons, right? And don't forget, bonds can rotate, right? So the more carbons there are, it's going to be a little harder to get that backside attack. So 1, 2, 3 makes sense. A little trick here. This is still a primary alkyl bromide, but then there's this big terbutyl group here. So there's some debate, right? Bromine's a better leaving group than chlorine because Br minus is larger, so it can stabilize the negative charge more. But really, we take both answers here. Probably not the best question. Next one, draw the molecular orbital picture for an SN2 reaction using one of the electrophiles above reacting with CH3O-. So, right, follow directions. Pick one of these guys above. I just took this one. I drew in sigma star because it said draw the molecular orbital picture. So there's sigma star, the nucleophile attacks, right, 180 degrees away, backside attack. As electrons go into sigma star, this sigma bond breaks, and that's the molecular orbital picture. So number 3 asks to rank the nucleophiles below in isopropanol. So you had to know what isopropanol was, which is a polar protic solvent. From strongest to weakest, so reactive to less reactive, at least. So as we were saying before, reactive to less reactive, polar protic solvent. First thing you want to look at, these are nucleophiles. So if something has a negative charge, it's going to be a good nucleophile. So obviously the things with the negative charge here are going to be better nucleophiles than not. The other question is then becomes S minus versus O minus. What's the difference? S minus is bigger, so it's going to be harder for it to be surrounded, right? So it's going to be more open and bare. So that's going to have a better nucleophile because it's harder to surround because it's bigger. For the other ones, so if we're looking at, we have an amide, a phosphorus, and an amine. So hopefully, usually with these rankings, if you can box it in, the amide you should look at it and say, wait a second, if we're talking about nucleophiles, we're talking about the nitrogen lone pairs. But that nitrogen lone pair, I know amides are really strong bonds. It can be bound up in resonance. That's not a good nucleophile. I've never seen amide be a nucleophile, so that should be the weakest. And then between nitrogen and phosphorus, again, we look at the periodic table and say, well, wait a second, which one's going to be more reactive, phosphorus or nitrogen? Phosphorus is bigger. So again, it's going to be harder for, right, there's lone pairs here, I didn't draw them in, but there's lone pairs there. It's going to be harder for something to surround phosphorus than nitrogen. So phosphorus is going to be a better nucleophile in this case. So in polar protic solvents, size really matters because it's harder to surround the bigger things. All right, for number three again, for the substitution reactions described below, pick the reaction type at 1 point each and explain why at 2 points each. So a pair of enantiomers becomes a pair of diastereomers. Ooh, wait a second. So a pair of enantiomers become diastereomers. That means what? They're both diastereomers now. What would that mean? So diastereomers have one that stays the same and one that's different. So a pair of enantiomers, when they become diastereomers, there actually has been SN1 reaction, right? Because it makes a carbocation, so it racemizes itself, right? So it has to go to that. I've changed my mind. I think this is a bad question. Ignore this question. I think it actually should be SN2. Or it could be SN1. It actually could be either. Either way, that could work. So, take it for what it's worth. A tertiary benzylic alkyl halide reacts faster than an allylic tertiary benzylic alkyl halide. That should tell you SN1 because a tertiary benzylic would be more stable, the carbocation would be, than an allylic because there's more resonance in a tertiary benzylic. You'd probably predict the opposite for a SN2 because a benzyl group, a phenyl ring is a little bit bigger than usually other alkyl groups. The reaction rate increases in dichloromethane. Dichloromethane is a polar aprotic solvent, so that makes me think SN2. The reaction rate triples was 3 times the nucleophile. That was the thing I had to change in the test, right? That'd be SN2 as well because, right, the reaction rate is dependent upon the nucleophile in SN2, and SN1's not. That was a tough little set of problems. Give the mechanism for the SN1 reaction below. Tertiary alkyl halide, first step, carbocation formation. Make a tertiary carbocation. Solvent is the nucleophile, it comes in and attacks. We form Br minus. Because there's so much solvent, there's more likely that the oxygen would attack, versus even though Br minus is a better nucleophile. More solvent comes along, takes that H. You form essentially HBr here and your new product. And of course, there's no stereocenter for 2 reasons. You went through a carbocation, and also because it never started out as stereocenter. I wanted you to do, from above, draw a free energy diagram of this. Right? So I wanted to see those intermediates. So that reaction coordinate, that energy diagram, the first step had to be the rate determining step because you're forming that carbocation. That takes a lot of energy. Intermediate A is still high in energy because it's a carbocation. Intermediate B is lower in energy, right? Everybody has full octets now. And then finally, the last little bit is that forming product. The tops of the hills are transition states. The valleys are intermediates. That's pretty much it. Give the mechanism of product for an E2 reaction below, right? This is your classic, it's a little weird. So fluorine, remember? Fluorine is not a very good leaving group. So fluorine, even though it goes through an E2, it goes through an E2-like mechanism. Technically, it's not it's not just like regular E2. You actually form an intermediate first. Right? Because fluorine is such a bad leaving group, you actually form a negative charge first, and then it comes down and kicks out. The other question you should be asking, well, why did you choose this hydrogen and not this beta hydrogen, right? Eliminations are always about beta hydrogens. Well, eliminating this beta hydrogen makes a conjugated system, which you always know is more stable. So it's a little trick. You know, it should be E2-like, but fluorine, because it's such a bad leaving group, right? You actually form that negative charge there first, and then it goes down.
So what would it look like if it was like iodine there?
If it was iodine, it would just be one step, and the iodine would fall right off. You still get the same. You still get the same product, but there wouldn't be an intermediate at all.
So you take the H that was connected to the, or that was on the same carbon as well.
Yep, the same. It'd be the same product, same H would be lost, except only difference would be is that being one step, not this intermediate.
Okay.
Yeah. Fluorine was like one of those weird exceptions we discussed. So this is your classic 7. Is your classic. Give the mechanism for the elimination of the product below. One thing you should be thinking about doing, obviously numbering your carbons. Always number your carbons. And also bonds, broken bonds formed. So you got an idea where you're trying to get to. So the first step you should look at and say, what kind of reaction is this? Do I have a strong nucleophile base, reactive nucleophile base? I do not. That's just methanol. So I should be thinking SN1 or E1. The first step of which would mean carbocation formation. Of course, this is a tertiary alkyl halide, so it's not like I could do SN2 anyways. So let's form a carbocation. It's tertiary, which is good. So I have a carbocation at 8. I could do a hydride shift and form a secondary carbocation, but it's not just any secondary. It's secondary and a allylic, which then the pi bond resonance can move over and get a tertiary and allylic carbocation, which then can eliminate and get the final product shown. Why favor E1 over SN1? Conjugation. Also, this is the product I told you to make. Make it. All right. Biggest things to take home here, rearrangements happen. And don't forget, secondary allylic is better than just tertiary carbocations. That again for you. All right. So here, the biggest key here is secondary alkyl halides. That means there cannot be a carbocation formation. No SN1, no E1. That means even though this is not a very reactive nucleophile, it's going to be an SN2. It's going to be slow, but it's going to be an SN2, which means, of course, inversion of stereochemistry. In this case, better nucleophile, secondary alkyl halide, it's going to be much faster, still inversion. Number 9, give the mechanism of product reaction below. What kind of reaction is this? You should see a bulky reactive base. Think it's a base. That should make you think of E2, not SN2 because it's too big. That means you have carbon 1 and carbon 2. You have a leaving group, secondary alkyl leaving group. You gotta look for beta H's. So you guys, I like to start rotating this to get the leaving group and the H in the same plane. Once you do that, you can do your mechanism. So the bulky base taking the H, anti-periplanar relationship. Electrons go there, kick out the bromine. You can see the methyl and this isopropyl are on the same side. And the hatched H and ethyl on the same side. That's why I like getting the same plane. It's easier to see what kind of alkene you have in the end. Second part asks for drawing a molecular orbital picture of this. So this involves showing those sigma stars. The base goes in the sigma star of the CH sigma bond, which then breaks this CH sigma bond. These 2 electrons go into the sigma star of this carbon-bromine bond, which in turn breaks the carbon-bromine sigma bond, giving us the alkene. You can see A and C are wedged on the same side, B and D are hatched on the same side as well. So 11 asks to show the ring flip for each and the product of the reaction below. So first step you have to do is the ring flip. The biggest thing with ring flips, of course, is if something was on top of the ring, it's always going to be on the top of the ring. But that doesn't mean if something's equatorial, as this chlorine is, it doesn't mean it's always going to be equatorial. So if you do a ring flip, what was equatorial becomes axial. But it still has to, if this chlorine, we think of this chlorine pointing up, it's still going to be pointing up in the product. So I like to pull down this, pull this up. This chlorine's now axial, but notice it's still pointed up. This methyl was axial, but it's pointed down, so that's going to be equatorial down. There it is right there. And the reason we do this is we need to get the chlorine, right? If we have a big bulky base like this, which is reactive, we need to get the chlorine axial so we can get into that anti-periplanar relationship for an E2 reaction. And then we also need to have the H that's beta to it must be axial as well. So notice the H on carbon 2 here is equatorial. So it's not anti-periplanar to this chlorine. So this H can't be eliminated, even though it's on the more substituted carbon. So we actually have to use this H as axial in 6. And we do our E2. And so you actually get the non-Zaitsev product here. Right, the non-Zaitsev product. You could also do an elimination of an H out here as well. I think that would be possible. Because this is a tertiary alkyl halide. The other one, ring flip again, same rules apply, right? Bromine's pointed down here. It's equatorial. That means it's going to be axial on the ring flip, but it's still going to be pointed down. But you notice here, it's a tertiary alkyl halide on carbon 2, and our base here is not very reactive. It doesn't have a negative charge. So this is actually going to be an E1 reaction because it's tertiary, so you actually form a carbocation. And then once you form a carbocation, it doesn't matter. You're not worried about the anti-periplanar relationship anymore once the carbocation forms. Now you're just looking for the beta H's to form the most stable alkene, which would be the most substituted. So you actually get a different product here. You get the more substituted versus up here you get the non-Zaitsev one. So depending on the mechanism, right, you can really control what kind of products you get. Bonus, what's the stereochemistry of the first R material and above? R. All right, so carbon 1, you rank it be 1, 2, 3, and it's R if you did the mapping. That's R. Trust me. All right, so looking at number 12, this retrosynthetic problem. First thing I would identify, you notice I've numbered the carbons. Right, the carbons have been numbered. 1 and 2, 1, 2, 3, 4, 5, 6. So first thing you look at here, you should write your notes. I've added 1, 2, 3, 4 carbons from 2. You only know so many ways to make carbon-carbon bonds. You know the way to make with Grignards. You also know the way to make them through alkynes, right? Actually, don't know Grignards yet. Maybe you do. I don't know. Alkynes is one way to do it. The other thing you should notice, these OHs are trans to each other. So that should tell you something. These two H's are cis to each other. That should also tell you something. To get a diol that's trans, you should be thinking about what star material does that come from. One step back, that's an epoxide. An epoxide is a way to make a trans diol. So you should be thinking about epoxide. Where do epoxides come from? And notice these H's on the same side. They come from alkenes. And a particular type of alkene here, the H's had to be on the same side. So it's a cis alkene. How do I make cis alkenes? They come from alkynes using Lindlar's catalyst, which only adds 2 H's, but they add them cis, right? I have an alkyne. Now, I know how to make carbons on alkynes. That's usually, I can break either side, doesn't matter here. You make those, so you make alkyne bonds there, break another bond there. That gets us to just acetylene, 2-carbon alkyne. How do I get that? So it has 2 pi bonds. That means I need to eliminate 2 things. So I need to have 2 leaving groups on there. How do I get 2 bromines on there? How can I get a trans bromine? I get that from an alkene. How can I get an alkene? Just 1 pi bond is just having 1 leaving group. Now going forward, to get an alkene, I need a bulky base, do an elimination. To have 2 bromines, I need Br2, no solvent, and give me 2 bromines. I add in a strong base, I do 2 of them, 2 equivalents of that. Right? I lose 2 bromines, I get 2 new pi bonds, double elimination. Once I have an alkene, a terminal alkene, there's acidic CHs, Strong base deprotonates 1. We can do an SN2. Strong base deprotonates another CH. Do an SN2. Lindlar's catalyst adds the H's cis. I can do the epoxidation with MCPBA. And once I have the epoxide, the H is on the right side, the methyl and the isopropyl are on the same side. Now I add an OH minus, it'll attack, and you get the less, and you get the, it would actually be on the other side, you get the enantiomer of this, but same difference. You get the trans diol in this case, start to finish.